All right, we are recording. Welcome to episode 13 of Roid Rage. Today, we have an outside special guest. That sounds weird. I'm going to say that again. We have a special guest coming to us from LBTO, which is Large Binocular Telescope in southeastern Arizona.
Is this our first external guest?
Yeah. This is our first external guest.
Oh man, pathfinding.
Oh, we'll see how this one goes.
I'm honored.
We'll see how this podcast ranks in
It's
Kenya.
not going to be smooth.
Yeah.
Well, Al, it's going to be hard to drag us down, so all we have is to go up from here. But the reason we wanted to bring on Al is because he has spent a good chunk of his career, and I'll let him tell his story in a minute, with ground-based telescopes observing asteroids. So he probably knows more about asteroids than all of our individual knowledge stack. But before we get into asteroids, Al, thank you for being on the show.
Or apologies.
Or apologies. We'll see. We'll check in at the end and see where you are. Who are you? How'd you get to LBTO? What is LBTO? Help the listeners out.
All right. Okay. Well, I was born on a dark and stormy night. I won't go that far back. Yeah, sorry.
You already fell asleep. Nobody cares about you, Al. Talk about LBTO.
That's not true. We care about Al. They want to know who's talking.
I'm gonna go with Chap on this one.
Yeah.
Okay. So I got into astronomy early on. My background was actually math. I was, at Berkeley. Tried to do the PhD in math.
I mean, I guess you got to go where you get in.
Yeah, kind of ran out of steam there. Got into computer science, and somewhere along the line, got really, really interested in studying the solar system. And so, first job was at Lick Observatory, which at one time was the largest observatory in the world.
Well, it's called Lick.
Yeah, Lick.
These
James Lick.
names. I don't care. That's
Yeah,
just
they're
terrible.
First you complain about acronyms. Now you complain about fun names.
Well, the next one was Keck. So they all had to be 4 letters ending in CK. That was part of the agreement. That was
an
in
agreement,
Hawaii.
Matt.
It was a great excuse to move to Hawaii. I still live in Hawaii. I used to work remotely. And then in 2010, I went to Germany and worked at Max Planck, and got more and more into using these telescopes to study asteroids. And now I'm at the Large Binocular Telescope. So I can tell you about the Large Binocular Telescope. It's, as the name implies, it's like 2 mirrors, but you don't use it like a pair of binoculars. It's just to get more glass on a single mount for collecting photons. Big telescopes are big for 2 reasons. One is to see things that are really faint. And the other one is to see more detail, to be able to resolve. So when you talk about resolving detail, reading a newspaper on the moon or whatever, you don't say, "Oh, I can resolve down to a kilometer," because obviously that'd be different. A kilometer on the surface of Jupiter or a kilometer at some galaxy is different. So you measure it in terms of angle. And with a larger mirror, you get to smaller angles, and we can actually go down to, so you don't measure it in degrees, you don't measure it in minutes, you don't measure it in arc seconds, you measure it in milli-arc seconds. And we can resolve down to with our latest instrument, down to 20 milli-arc seconds, which translates to about 80 kilometers on the surface of Io, for example, or on Jupiter.
What is? Give me a reference here, though. Like if I go buy a telescope from Target, what is it at?
Target doesn't sell telescopes.
Okay, Walmart.
What resolution can you get?
Yeah, like what is an? If I have a normal 3-foot telescope that everybody has on the patio, what is that resolution?
You don't have to go very big until you can get down to whatever, let's say 1 to 3 arc seconds if you're on a good site. So if you're on a good site like Mauna Kea, for example, is one of the best sites in the world. Atacama, Paranal and Chile are the maybe second or equal good sites. You're going to, just from the atmosphere, be able to only be limited to an arc second. So the thing about ground-based telescopes, it's different than space, is that you're limited by the atmosphere.
Hold on, I got so many questions. So what's a good site?
Yeah.
Is it just that it's high?
Yeah. So it's not so much that it's high, it's the kind of conditions you get when you're up high, which is dry. That's kind of a good thing. But it's mostly this thing called the seeing. And that's the thing that I just mentioned, limits you to like an arc second. So Yeah, tell me if I get too technical, but there's the atmosphere is you can think of it as broken up into cells, and each of those cells kind of distort the light a little bit.
Okay.
And they aberrate the light, so
Yep.
the light from your galaxy you're looking at far away travels all these millions and millions of light years, and then it just in the last few milliseconds, nanoseconds, as it goes through the atmosphere, gets aberrated, which is why people build larger telescopes. And the amount that it gets aberrated is called the seeing.
Okay.
And it basically is the size of those seeing cells, Fried cells, whatever you call them. And so on a really good site, those cells will be like 20 centimeters to 40 centimeters. So if your telescope is 20 to 40 centimeters without adaptive optics, you're going to do just as good as a 100-meter telescope. Because in terms of the angular resolution that you can see, it's being blurred by the atmosphere, and it's being blurred to the level of about an arc second on a really good site. If you just
Wow, so this is like awesome, like Christmas gifting technical knowledge on astronomy telescopes, right? Because like if all you're going to do is transport in Matt's car a telescope, over to like I don't know, let's go out to like Joshua Tree or Mojave Desert or something, right?
Spot.
Like it's a dark spot.
Deserts are good. Yeah.
Deserts are good. Matt likes to run. I don't think he likes to run up mountains and shit. So we'll just stay on the flat desert plain. So buying anything bigger than you said, like 20 centimeters
40.
aperture is kind of a waste of money.
So why is if that's true?
Again,
What's that in freedom units? I got to do the math.
There were two reasons, right? It was to see more detail.
Yep.
Then you're wasting money getting a bigger telescope more than 40 centimeters, unless you equip it with adaptive optics. I mean, adaptive. Yep. So
what are adaptive optics?
Okay, so it's basically a rubber mirror, flexible mirror. So you and it started in like right around the turn of the century.
Okay.
And I first started working with adaptive optics around 2005, and so it's you sense you have a fairly bright source,
Yep.
star or whatever, and you sense the aberrated wavefront. So the wavefront, after it's traveled millions and millions of miles from the galaxy, is perfectly flat. Then it hits the atmosphere and it becomes like a potato chip, kind of wrinkled.
Yep.
And the goal of adaptive optics is to flatten it out again, to get rid of that aberration.
Okay.
And so what it does through the miracle of computers, it senses the shape using what's called a Shack-Hartman array or a pyramid wavefront sensor, and it digitizes the shape. Okay, it's called slopes.
So you're just estimating you're estimating the attenuation through the atmosphere and then just correcting for it on the mirror?
Measuring it. We're measuring the attenuation, and so you get from this wavefront sensor, you get like a map or 3D a measurement of that aberrated wavefront. And so all you got to do is take the reciprocal of that shape and put that shape onto a mirror that with piezoelectric underneath can be deformed as small deformations, and it's just like magic. The potato chips go in and the flat wavefronts come out. I tell you, it's just like putting on spectacles. I mean,
I love how you said all you got to do is just take the reciprocal and then
just take the inverse square root and then you're good.
A piezo actuator.
Hold on, I got a question though.
Oh my God.
Okay, so you're saying we should never build I feel like I'm missing something. So you're saying there's no reason to build a telescope over 7.8 inches or whatever, right? Because you can't
there's
resolve.
Totally a reason to do it. And that's it. Remember,
what am I missing then? Yeah, why?
Well, because you're not always just trying to see things more clearly. You see more detail. You're often like trying to take spectra of a galaxy really far away. And that's, for a lot of people, that's why you build big telescopes, is to understand the big questions, cosmology. And it's not to be able to read a newspaper on the moon. It's to be able to take spectra. And for that,
all right, Al,
it's a light bucket. You're just collecting more photons.
I know this is not going to come as news to you.
Yeah.
We don't really care about galaxies.
Yeah.
And like the moon is kind of cool, but like
right.
reading not even yesterday's news, like
Right.
The moon's a distraction.
yeah, the moon
Right.
the moon is like, I mean, did we put like a never mind.
We did
But
not
it's
hit the moon.
ironic. I think for trying to find an asteroid that's got platinum group metals, you're not going to use adaptive optics. You're going to use the big telescope because these asteroids are really small and so they're really faint.
Yep.
And you just need the photons.
Just
Did
the
you
So
go
then,
spectroscopy.
critical
So,
question is:
yeah.
is LBTO adaptive optics or not?
It's both.
Okay, good answer.
All
so we
right.
can
All right,
use it.
yeah.
Good enough.
It's whatever you want it to be. It's
a
everything.
little more adaptive optics than any other telescope. I mean, one of our revolutionary technologies is, the telescope has a primary mirror. That's the big one that you say,
That's
we're
the expensive one, right?
We're a 10-meter telescope, right?
Yep.
Or we're an 8-meter telescope. Or in the case of LBT, we're kind of a 12-meter telescope in terms of the collecting area. And we're kind of a 23-meter telescope in terms of the actual width of the thing. So for seeing more detail, that 23 meters is important. Then light bounces up to the secondary mirror.
Yep.
And then it goes down to the tertiary mirror, and then that feeds all the instruments.
Okay.
And LBT is the only telescope in the world. That's not true. The Europeans are caught up. They've got one, and a couple others are in it. But we have our mirror that can deform and take the reciprocal of that potato chip and turn it into a flat thing, is our secondary mirror.
Okay.
So basically, all the other adaptive optic systems, they've got like a little mirror inside the instrument itself that does the correction. But since we do it there, all of our instruments have the potential to be using adaptive optics. But truth be known,
Because that's because the main mirror itself is adaptive.
Yeah.
Secondary, Matt.
Yeah.
Pay attention.
Well,
The left or the right mirror?
both.
Both, Robin.
Oh, thanks, Matt.
And I was going to say something really important there, but it's gone.
And welcome to Roid Rage.
Actually a part of the podcast.
I got another question for you because I'm just curious about this. So I watched this documentary on how we dramatically screwed up Hubble, which is always comical, right?
Oh, right,
That had
yeah.
adaptive optics on it, apparently.
Yeah, astigmatism.
I look at these pictures of LBTO and it's like just these giant mirrors sitting in the open atmosphere. How do you guys deal with dirt getting on them? Or it's, there's pine trees in front of these, like pine leaves and birds. Like, does that
Cell
mess
phone
up your mirror?
antennas.
Yeah, definitely. Yeah.
What do you do?
We clean them.
But does it scratch it at all? And are you guys concerned with that? I mean, it seemed like
it's not scratches so much, just the stuff you talked about, dust, dirt, ash. And so, but it doesn't really affect the image quality. It just affects, it makes it a smaller mirror, it affects the reflectivity. And so, you might as well have, if you've got a 10-meter mirror or if you've got an 8-meter mirror that's so dusty that you're only getting 75% of the light, you might as well have a 6-meter mirror, that's clean.
Got it.
So yeah, it's just.
So it really doesn't affect your ability to actually see images other than by essentially making the mirror smaller.
Yeah, we re-illuminize them. We shut down in the summer for 2 months because in Eastern Arizona, you have this thing called the monsoon season, and it rains so much that it's not really practical. And so we shut down totally, take everything apart, clean it, put everything back together again. And so every 2 years, we illuminize one side, and then in the off year, every 2 years, we just thoroughly wash and clean the other one.
You said you take it apart?
Well, we tend to take a lot of the instruments apart.
Oh, the instruments, not the mirror.
No. Well, we take the mirror off.
You take it off?
Huge. Yeah.
You ever drop it?
No. Well.
Oh, this sounds like a story I want to hear.
Previous telescope. No, never at LBT. And it,
yeah, I mean, totally.
Hold on, you can't leave us there. When did you drop a mirror?
I never dropped one personally.
Have you seen one dropped?
So different. No, it wasn't dropped. It was, picked up improperly, cracked a little bit.
Ooh, cracked a
It
little
was
bit.
a long time ago. It's ancient history.
What telescope? Call it out, Al. You got to let us know so we can go look it up.
How many listeners do you have?
Like 50. Nobody listens to this shit.
It was. I mean, it was a telescope that was made with hexagons. Okay. So that it's very much.
Did it rhyme with James Webb?
No.
Okay.
No, James was in space. No, it was one of the ones that ended with CK that I was talking about earlier.
Super helpful.
Wow.
On the note of telescopes, like
Dancing around.
understand that from LBTO and the atmosphere and the attenuation. Is that the only reason we send something like James Webb and Hubble to space, or why do we send telescopes to space?
It's mostly that. It's mostly to be above the atmosphere.
Okay.
Yeah. And so, and you don't have to do adaptive optics. And adaptive optics is almost as good. In fact, I'll show you later when we do the talk. You take an image of Eo's volcanic moon Io, Jupiter's volcanic moon Io. Our image from LBT is about 3 times sharper than the one from Hubble. taken at the same wavelengths.
Has James Webb taken an image of that moon?
Yeah, it works at longer wavelengths. So you don't get the stunning, I mean, that's the other thing that goes into angular resolution is the wavelength. You know, the longer the wavelength, the less the resolution. So JWST tends to work out at like 4 or 5 micron wavelength, and in the visible you're down to like half a micron wavelength in the middle.
So James Webb has less resolution just because of the wavelength, but can see further.
It has less resolution because of the wavelength, but it's in the thermal. You learn so much, especially about like exoplanets, looking at the longer wavelengths. So you can't always just be going for resolution. It's like, where's the science? And but also it's a smaller mirror. It's not an 8-meter mirror. It's a 6.5 meter mirror. And so we're effectively a 12-meter mirror. So we're going to just be able to get higher angular resolution, even though we're on the ground, because we got adaptive optics.
So Al, now that we have this adaptive optics technology, why do we send any telescopes to space? Why not just build them all on the ground?
Well, it's a fair question, and I think they basically complement one another. And I've got plots and stuff. Roughly, it seems like going way back, 10, 20, 30 years, that the space-based telescopes, the diameter of the mirrors tend to be about 1/3 the size of the biggest ones on the ground. So, we're coming up on an age of like, 25, 30 meter telescopes. And right now we got a 6.5 meter in space. And so it seems to be following, the Hubble is 2.5, and that was the era of the 8 to 10 meter telescopes on the surface of the Earth. The images you get from space are better than the ones that you get with adaptive optics, slightly or somewhat. And so there'll always be a reason to put telescopes in space.
Is anyone talking about doing like interferometry above the radio spectrum? They did those amazing black hole pictures, right? Using the whole Earth from around
using the baseline of the
Earth. Using the baseline of the Earth from multiple telescopes and all that. But of course, that's at a much lower frequency, right?
Interferometry. I think in terms of wavelength. So a much longer wavelength.
Yeah.
And so the certainly interferometry. So I mentioned earlier that the two 8.4 meter mirrors are separated by edge to edge 23 meters. There's like a 7-meter gap, and then you got the 2 8s. And when we phase the light coming into both of them, which we do like about 20% of the time, then we're doing interferometry.
Yeah. That's what it sounded like.
Phasing, yeah.
So on LBTO, can you just add another mirror and make it even bigger? Like, is that a plan just to make it, a trinocular?
Trinocular telescope?
Yeah, trinocular. That's a word.
Is that actual
It's
word?
Funny because we had to like outlaw that word. There was this thing where
it's a real word, chat. I told you, it's just an outlawed word.
Yeah, we
see if that's in the Scrabble dictionary.
We had this thing where we could, on one side, we could use 2 instruments simultaneously by separating the wavelength. This one takes the visible, this one takes the infrared, and so people were calling it trinocular mode. And we finally had to stop because people were mad. It's not really trinocular, but no, kind of yes and no. So the Giant Magellan Telescope is like LBT, but instead of 2, it's got 6.
Is that the one that's in Chile?
It's good. It's being built in Chile. Yeah.
That's the one we have to do all that complicated like underground light tunnels to combine it. I watched some History Channel documentary on this.
No, you're thinking of the VLT, which is in Chile, which is 4 8-meter telescopes. So sort of like us, we're 2, but our 2 are on a common mount. Okay, so we're really just like a sort of one telescope. The VLT is 4 8-meter mirrors, and they're separated by, between like 50 and a couple hundred meters each, and they have all these tunnels underground to combine the light.
Why'd they separate them?
Interferometry. Well, it's they built 4 telescopes to mostly just have the duty cycle, so they could do like 4 times as much science, but then it also has this capability of doing interferometry, and it's kind of a mixed bag. I mean, the further they are apart, the higher the resolution you can get, because that baseline
that's what I'm talking about.
Determining resolution, and then you get like micro arc seconds. Really, really fine resolution. But the further they are apart, the sort of harder it is to do. You have to take a lot more images in order to get an image that you would get of a round telescope that had that same.
Because you just don't have as many photons.
Yeah, they call it filling in the UV plane. It's like you have to observe the thing that you're observing at lots of different times in order to effectively fill in all that space that's missing in between the two. Yeah.
What is sorry, you brought up the Large Magellan Telescope. What? Giant Magellan, whatever.
And the one in Europe, the Europeans are extremely.
Hold on, so it's the
there's
GMTs.
one on the book called Overwhelming.
I just love looking over at Matt, and he's got this look of like, I have no idea what Al is talking about.
Is just very large telescope.
Good call. Yeah.
Wow.
So we started to go from 4 letters to 3. So the GMT.
Well, it's like we have UHF and VHF.
Yeah, just like
for
super
radios.
pragmatic.
Yeah.
Just, you know exactly what you get.
That's true.
What is the GMT? Is it the next best thing in telescopes?
Greenwich Mean
One
Time.
of 3. It's a big shootout going on between the next generation. They're all in that 20 to 30-ish round. Europeans are definitely winning. They're
Cool.
Whoa.
459 billion.
Just
Wow.
throwing it down.
Sorry,
Good job, Europe.
So yeah, tons.
Do we have to pay tariff on data that we get from the Europeans?
No, the
That's for a
penguins.
government
Penguins, maybe.
All right.
So it's like, it's many, many billions of dollars. It's being built in Chile, and 39 meters. And it's, if you Google it, they're building the structure. You can see the framework of the dome.
Yeah, it's like
pretty
one of those
far
big
along.
construction projects, though, that you don't get a sense of scale unless you see a person in the picture or something.
Yeah,
Because
that's
it's
right.
like obscenely huge.
I mean, even these like giant cranes look tiny.
Yeah.
Building.
It's like a rocket, right? Like you don't
Starship,
understand a rocket
it's
till you
just-
go stand next to it and you're like, oh shit.
Yeah, and then you go stand next to Starship and you're like, oh, I thought I knew rockets were big. No, I didn't know.
Going and looking at the Saturn.
Yeah, Saturn V, same thing,
In
right?
Houston, laying on the ground there.
Yeah.
That's still
Obscene.
for me.
Yeah.
Anyway, so there's that. And then there's the 30-meter telescope, which was
So wait.
Yes.
So of all these telescopes,
Yeah.
like if we want to look at some of our target bodies, like how much in advance do I got to ask for permission, and how much money do I need to go ask Matt for? Like what's it take?
the conversation got right to where I want it to be. Yeah. Anyway, well, there's 3 mechanisms. So one is director's discretionary time. And so
That's what Al's
sounds-
giving us.
Yeah, I was gonna
Yeah,
say
so
that
that's
sounds
what-
like a really. I like that one.
So
Discretionary.
we've done
That's-
that, but it's kind of limited.
Yeah.
And you're supposed to, it's theoretically kind of reserved for, well, something happened. And in order for me to observe it, I can't go through the regular proposal
So, like,
cycle, which is
Unami.
months long.
Unami, umami.
What are you talking about?
Oumuamua.
Muamua. Oumuamua.
Interstellar visitor.
Yes.
Absolutely.
So that would definitely be
that was
discretionary
all
time.
totally studied by.
I feel like I'm aged out of this
discretionary time.
conversation. I have no idea what you guys are talking about.
This was the object that we think came from another.
We don't just think. Yeah.
Yeah.
Yeah,
It
no.
was a parabolic.
Way to just slap him down.
Oh,
we don't
Sorry.
think. We know.
I'm sorry.
Excuse
That
me,
was rude.
flat
Wait,
earther.
wait, wait, are you saying that
we don't think that.
aliens
We
are
know
visiting
it.
us?
Well, talk to Harvey Loeb or what? No, Avi Loeb at Harvard University. But yeah, no, he's the radical guy that says because it did, it.
Yeah, no, it's
it-
Arthur C. Clarke, man. It was the cylinder.
But the ruling wisdom is it's an asteroid, but not from our solar system. Came from outside the solar system. First interstellar object. But it accelerated. It was kind of non-Keplerian motion on the way out. And so it's like,
Well, it already left.
Yeah,
it
it's
was-
gone.
Yeah. Well,
What year was this?
gosh.
A couple years
2
ago.
Yeah, it wasn't that far.
Yeah.
Do you not read the news?
Apparently not.
Yeah. Okay. Whatever.
Yeah.
All right. Let's get back to. I want to like. I need
Hold on,
a
it accelerated,
observation
so
quote.
A
We
little
think it had some
bit.
thrust.
Like
There was aliens, or is
no,
there,
it's the
is there
whole,
a
like,
scientific explanation
mod.
for it? Or
Yeah.
is
Well, now they're
are
saying
bodies
relativity's not
that,
right.
That accelerate, that go
Comets?
around the sun, and those are the comets, right? They're outgassing, and they get a little thrust from that, and so that's the wisdom is that Oumuamua was a comet, But there was no tail. Nobody could see any tail or anything.
I need a cost quote here. So we got discretionary time, got that
Okay.
one.
And then you got the regular proposal cycle. 3 months before each 6 months semester, you write your proposal, and it goes before the time allocation committee, and they just tell you whether you get time or not.
Does that proposal have to be science-based? Could it literally be, we want to go look at asteroids and we submit a proposal?
Absolutely, absolutely. And we'll talk at the end of the day, but I'm hoping to write a proposal that would, for the.
Oh wait, I don't even have to write it. You get to write it.
Yeah, I've written lots of observing
Oh,
proposals.
that's even better.
I've
So
got a pretty
this
good
is
track
great.
record.
Yeah.
Okay,
So-
cool.
All right,
Better than our
I'm
track
just-
record of 0.
Yeah. I think every semester we should get a proposal in there. And so, yeah, yes.
Like
there
semester
has
is
to
like
be
a. I just want,
scientific-
is it
there
like a
has-
school semester, or is it like a semester like in a different context?
It's in a different context.
Okay.
We're down 2 months in the summer,
Yep.
shut down. So there's
Yep.
2 5-month semesters.
Okay.
They're just the name of the year, AB. So,
Got it. Okay,
So the one coming up is 2025B.
Okay.
And so
it's like a classroom.
right.
25B.
Yeah.
School of the universe.
Got it.
School of the Universe.
All right, and there's a third.
There's a third, and that's you can purchase telescope time.
Okay.
Oh, that sounds.
Actually,
No, we're
it's-
not doing that. That's really expensive.
It's
How much?
Not that expensive. It's you go to the website, and so you should get the official from the website. You go to LBTO, and right on the top there, it says
We're gonna fact check you.
access to LBT,
Actually, I'm going to use ChatGPT though.
and there's a table, and it says here's the 3 ways that you can effectively purchase. You can become a member. That's the platinum.
So I have to buy a member. You guys are like the B2B
How
SaaS of
much?
telescopes.
Well, I
Does
don't think you
time
want to go
on the
with
LBTO
you
cost?
could be a member.
ChatGPT.
You could have like long-term programs, or you can just buy some nights. But probably
Oh, you could
this
totally
isn't-
buy a night up on Wilson. They sell it
No,
like
it burned down, right?
oh.
And yeah, tell me what it says down there in the and it has one column is the cost.
All right, full membership. It says 25 to 30 nights per year per 8th share.
Yeah.
And an 8th share, Matt, you ready? Okay, this is full membership. I'm sure there's a
Okay, so 25 times 8, 1/8, 25 times whatever number you're going to tell me.
no. This is the number for 1/8.
You're now a 1/8 partner in the telescope. You get 1/8 of the night.
Which
So I'm
basically gives
buying
you 1
1/8
month.
of the telescope?
Yeah.
1/8
Can I
of the
advertise
time.
on that building?
probably
I mean, that might be
everything's
sick, right?
negotiable.
Like,
No one's looking at the building.
Everything's
the building's
negotiable.
looking out.
when I Google this telescope, it shows me the building. So let's put AstroForge on the side of the building.
You're not going to want to do this, Matt.
How much?
It's 1.8 million per.
Wait, hold on. This telescope costs $120 million
eighth inch
to
shares.
buy, and I can get an eighth of it for $1.8 million?
But wait,
This sounds like a deal.
10
What am I
nights,
missing?
time purchase 10 nights. So that's the membership. That's the country club level.
right.
The time purchase is like 50 to 90 a night.
I don't understand this then.
50
So
to 90K.
I buy 1/8 of the telescope for $1.8
That's
million.
1,000, 90,000 to.
Check out footnote number 7.
Oh, footnote number 7. Sorry, scrolling. Oh no, I don't. Because I went to ChatGPT,
Dude, this is a
so
great
it's all
deal.
that stuff.
Oh, yeah.
This thing has depreciated a lot.
Anyway, the footnote number 7 basically says everything's negotiable.
Oh, wait, we can even negotiate it down.
Yeah.
Gotta leave
Auction
that.
time.
Yeah.
So in terms of
We'll give you $50.
in terms of a number of how much would it cost for you to tell me whether or not an asteroid has platinum group metals?
I mean,
It would depend a
there
lot
you
on
go.
when you
went
observe it.
exactly where I wanted to go.
Yeah.
Thanks, Al.
It would depend a lot on when you want to observe it. So,
Got it.
For example, if you look at 2022 OB5, for example,
Just a
right
random-
now it's like
just a random.
26th magnitude. We can't even hardly do it.
What can you see? What magnitude can you see up?
We can, there's 2 numbers, one for imaging, one for spectroscopy. For spectroscopy, we can go pretty easily down to 22nd magnitude. For imaging, 26th. When we imaged OSIRIS-REx when it flew by the Earth, it was 25th magnitude. So
25th.
yeah,
How close was OREX to the Earth when it
11
changed its
million
name?
miles. Oh, when it changed its name?
Didn't it become Osiris Apex?
Oh, no, that was the extended mission, I think.
But then it flew by the Earth, right? It's on its way to it's on its way to 1998.
That's such a
flew
crafty
by
thing how they
26.
probably got
It
that
might
through the
have done another
budgetary
gravity
cycle by
assist or
like, oh,
anything.
this isn't the same mission. This is Osiris Apex instead of
No,
Osiris
but
Rex.
this was the gravity
budget
assist on the
line
way to
items.
Bennu. It was 2017.
Oh, okay.
Yeah. And we imaged it was like 25th magnitude.
Oh yeah, duh. It's not coming.
Okay.
It's going to come back by and view Apophis.
Yeah, that's right.
That's what I'm thinking of. That hasn't happened yet. So you didn't image the future.
Correct.
Okay.
I mean,
Sounds kind
I would buy that
of
for
sounds kind of
$120.
limiting. You can only image the past. What's
Yeah.
up? Come on, Al.
Present.
Well, it's technically the past, right?
Well,
Because
it's
the light
technically
takes
the
a while.
past. It's always the
that
past.
one was the past, but we can image the present.
No.
Anyway, so
All right, there's a whole YouTube.
AstroForge
in terms
discovers
of
time.
how much it would cost for us to let you know whether a given asteroid had platinum group metals, it totally depends on when we observe it. So that's why I think we got to get ahead of this and be doing observing proposals.
We'll take the night shift.
So, for
We're-
example,
it's fine.
2022 OB5 right now is like 26 magnitude.
Yep.
Can't even, hardly even do it. It's just at our level, at our extreme of imaging. In about 7 months, it's going to be 8. And in about 3 months, it's like down to say 22 magnitude. It takes us like 3 hours. We have to stare at it for 3 hours to get enough photons.
I love that he already knows the magnitude.
Well, I was just looking at it as an example.
Yeah, I'm just saying.
Yeah.
Anyway, in January 26, it's 18th magnitude. We can do it 5 minutes.
Wow.
So it's all, and these things are on roughly.
And you get a spectrum off it, right?
Yeah.
And that'll legit.
Yeah. And so if it's nice and flat and rising a little bit to the red, it's like, oh, yeah, it might be PGM. So, so half an hour of time, it's negotiable. What did the website say was per night?
1.8 million plus.
No.
No.
Per night.
Per night
Per
is
night is
$50,000 to $90,000.
Okay, so let's take the 50. Okay. And they're 10
Great.
hour nights. Okay. So an hour is $5,000. And we can do it in half an hour.
So like $250.
2,500.
Yeah, I dropped
2,500?
This is a negotiation now.
So
I'm gonna
we're in the negotiation part. 300.
All right.
It helps me bad at math when you do negotiations.
Wait, so so time decreases with magnitude. What do you get back? So like we say, great, we're going to be generous. We're going to give you $500. What do we get back in return?
You get the spectra.
What is spectra?
Oh, sorry. It's
That's the name of a movie.
spectral energy distribution. It's the amount of flux at different wavelengths. So you got wavelength across the bottom, you got flux on the y-axis, and it makes like a shape.
Okay.
It's a rainbow. Sorry. I mean, that's the thing I always say. It's like when you disperse the light into a rainbow. But then you quantitatively measure it, spectroscopy, and then you have, a nice little plot at some spectral resolution. And we have more than enough spectral resolution to get that broad shape that would, to me, the ones you want to throw out is any kind of a little wiggle or bump, any kind of signs of silicates, or you just want that kind of metallic, reflectance spectra.
This is something we should talk with our next week guest about, because I don't have no idea what to do with that. You'd give us a cool chart. I'd probably print it out and put it on the wall, but we have no idea.
You compare it to spectra from meteorites from the lab. You compare it to.
You got to go talk to the science team more, Matt. Stop yelling at them. Start asking questions.
How consistent is the observation community on what actually constitutes an M-type?
Excellent question. One thing is they've changed.
You looked that up.
Did not.
Chapman's gonna
I think we've actually had this conversation before.
Yeah. Oh, yeah. Maybe we did.
Yeah.
Oh
One of the
yeah.
students-
Oh yeah. Let me just throw you a nice wiffle ball here. All right, go
I'm
ahead.
just softening them up for
Yeah.
the negotiation.
Yeah. Go ahead.
It's it's definitely debated. They've changed the names, by the way. I mean, M-type, is what was used a lot. Now there's X-type, which includes the metallic.
Yep.
But the three different X-types are different by their albedo. But if you're in that kind of brighter albedo, shiny, X-type, then that's called an M-type. Do M-types really? Are they metal?
Yes.
Mission Psyche tell us a lot. There's a lot, but yeah, it'll.
Yep.
I mean, that's the first, to my knowledge, real in situ investigation of what.
Yep.
These bodies that we see the spectra of remotely and call them M types.
Okay, last question I got for you, Al. I want to know on a personal level, do you believe in aliens?
Get this one a lot. I think that there's the Fermi paradox. Everybody know what the Fermi paradox is?
I think everyone in this room does,
But probably
but
not. Our
probably
50
not every one of
Actually,
our.
probably they do, but please explain it.
Yeah.
Enrico Fermi was sitting down with Edwin Teller and all the other guys at Los Alamos, and he was, a funny guy, and they were talking about the Drake's equation, and oh my God, there's so many, solar systems, there's got to be extraterrestrial intelligence. And Enrico Fermi said, "Where are they?" And that's the Fermi paradox. And so, yeah, I'd say my answer to the Fermi paradox is just the distances, wormholes, sure, yeah, right. And, faster than light, yeah, okay, maybe. And so, it's just, things are just too far away. But yeah, is there extraterrestrial life elsewhere in the universe? Yeah, yeah.
Yeah.
And
Sounds like Al's a yes for aliens. That's what I heard. Yes.
Well, and what's
Dark
alien intelligent life?
forest.
Was it K222b? Did you follow that one?
Yeah,
they
yeah.
found- that
Matt
could-
doesn't because he only likes real
I
names.
actually read about this one. But,
Oh,
all right,
you
fine,
did read the
Robin.
news.
Anyway, could be life right now, but no.
Do,
But
wait, do I
there's
do I
other-
get a last question, or
I
is
think we
Matt the only one?
we should all get a last question.
Well, I mean,
All right.
that was the last. How can you have a? I already asked the last question.
That's your last
Well,
question.
that's your last question.
Relative to you.
All right. If you've listened to any of our podcasts, Al, you know that we've been distracted by Tom. The act. I'm never letting it go, chap. Has anyone ever told you that you are like a doppelganger for James Cromwell?
Is that the actor that was like in the movie about the pig?
Yeah. Oh, I don't know about the
Babe.
pig one. I don't know about the Babe movie,
And he
but
played the president. He played the president.
yeah, Sum of All Fears. He was the
Sum of All
president.
Fears.
Yeah,
I
yeah.
just saw that.
That's a great
Yeah,
movie.
That
yeah.
holds up. That
Oh,
holds
yeah.
up.
Yeah, it holds up pretty well.
All those like '90s like CIA thriller espionage movies hold up.
Now you need to go raise money, Matt. You don't need to watch
10,
movies.
10 years ago, when somebody pointed that out, I was kind of horrified. Now I consider it a real compliment.
Oh, okay.
Go to Hollywood and like take a picture next to a star and just
Yeah.
like live it up.
Yeah,
It's a good one.
I should.
All right, chaps, show that up. Aliens and doppelganger
I'm taller.
actors. What do you got?
Yeah, you are pretty tall.
You are pretty tall. Do you have a favorite asteroid and why?
God, that's
That's a tough one.
Thanks, Chad.
Yeah. What's my favorite asteroid? I've got an asteroid named after me, and they let me name the satellite of it after my wife.
And that's not instantly your favorite asteroid?
That took you a minute? Oh, wait a minute.
He hasn't even told us his favorite asteroid.
Many places to go. Wait,
I
you
got an
named
asteroid named after
the
me, but it's
asteroid
kinda
after
boring.
you, but your
And I got
wife
the
is the
name-
moon,
I got
not
the-
the other way around?
It's a binary. They're sort of equal size.
That sounds like a little bit of math, Oh,
That's-
there's this. Air bars.
But the moon, I mean, it's,
I asked her scientifically,
yes, all right.
the most
Yes,
interesting
science,
asteroid
engineering,
for me is
math.
probably. I'm just going to go with Vesta.
Okay.
It's got that big chunk of it knocked off the bottom. It's got the Howardites and the HED. Meteorites, and it's. I don't know if you read just recently. They don't know whether to even call it a dwarf planet anymore because it's.
Oh, I
doesn't
don't want
have
to
a
talk
core.
about that. They're changing their definitions all the time.
I
Oh,
don't
this is a
read it.
dwarf planet. Oh, it's a minor planet.
Everybody hates
It's
the
an upwheel
IAU.
planet.
Everybody
Like,
hates
whatever.
the IAU.
Yeah.
But somebody's got to do it.
Sorry.
No, somebody does not have to do it.
Can we go
Pluto's a planet.
How does one get an asteroid named after oneself? Just hypothetically.
Chap's just like,
Just curious.
I'm just asking.
Yeah.
In my case, it was Bill Merline. You lobby to the IAU.
Can you take notes on that, Bill Merline? Let's hit him up.
He's
Yo,
a great
Bill,
guy.
we need an
Let's
asteroid
get
named
him
after us.
as a
Glad I got to
guest.
plug Bill. Bill's the greatest guy. He's the one who got me just observing asteroids. Remember when I said it earlier, and now it's gone? The adaptive optics, it's too long of a story. We're wrapping up. But for next time.
We got time for a story? Yeah.
Well, it's just kind of a technical, that's not an interesting story. But we talked about how adaptive optics allowed us to see resolution below 1 arcsecond, even though the atmosphere is okay. So prior to about 2005, you could only see shape down to 1 arcsecond. Well, Ceres is about an arcsecond.
Okay.
So basically, you couldn't see the shape or size or anything directly of any of the main belt asteroids before adaptive optics. So it was just like the sweet spot. But once you could go down to 50, 20 milliarcseconds, 20, 30, 40 times higher resolution, all of a sudden there were these hundreds of asteroids that we could now see the shape of, look for moons. If you can get both the shape and the moon, you can get density because the moon gives you the mass and the shape gives you the volume. And we could get density and composition. And Bill helped open that door. I was the technical guy with adaptive optics. So,
Sweet.
yeah, that's my story.
Let's get Bill. What's his last name?
Merline.
Bill Merline.
I bet he'd come on if we bought a full membership.
Well, we negotiated it down to $50.
$500. Yeah. Right. Yeah.
Could happen.
Awesome. Al, thank you for being our first guest. Really appreciate this.
I enjoyed it.
Thank
it
you
was
for
awesome,
listening
man.
to
Thank you.
Our episode of Roid Rage.